Ferdinand Ihringer from Shenzhen Tech to tell us something about Boolean functions on Grassmann graph.
Thank you very much for hosting me here for 2 weeks. I give this talk from time to time, but I think only Hong has seen it before, so it should be fine. I apologize if anyone else saw it. And what am I talking about? I want to talk about Boolean functions. And mostly I will talk about polynomials. And here you have the easiest polynomial, an affine function. You will all agree that you can see an affine function here. And what do we care about? For any set, input set D, we say a function is Boolean if it only takes 2 different values. Throughout my talk, these values will be 0 and 1. In some contexts, you prefer -1 and 1. It does not really matter. Okay, so what is the question? The question is, if we ask for Boolean affine functions, what do we get? And as an easy example to start, if we look at the hypercube, what are the examples we can have? So this is all over the real numbers, and our input are the elements of the hypercube, and we want to figure out which functions there are such that it is Boolean. Now, an easy example is we can take the constant function, which is always 0 or always 1. That's very boring. Slightly more interesting is this function, where our function depends on precisely 1 variable. So here, this function is 1 whenever the first input coordinate is 1 and 0 otherwise. Okay, that's nice. We only need to know the first coordinate to determine the output of our function. And of course, we could also take the complement. That is the same. And then I have to use that I have 3 blackboards here. We have these 4 examples. Constant functions, something that depends on 1 coordinate. Okay, and do we have any more examples? No, we do not have any more examples. We can show that on the hypercube, it must be one of these. And the proof is very simple. Some people claim in each talk you give, you should include at least 1 proof. And here I include kind of a proof. Without loss of generality, we can assume that for the all 0 vector, we get 0. So we figure out that the C here must be 0. Without loss of generality, we can assume our function is not constant. So at some point, it flips to 1. So one of our coefficients has to be 1. And now it's easy to figure out that all the other coefficients must be 0. Okay, so this problem is not very interesting. We have solved it completely. But I mean, you can ask for larger degrees. Say, here you have a degree 2 function. It is 1 precisely when the first 2 inputs are 1, and otherwise it's 0. And maybe now you hope maybe for degree 1 we had everything depends on at most 1 coordinate. Maybe for degree everything depends on at most 2 coordinates. That is not the case. You can write down more complicated things which depend actually on 4 coordinates of the input. So this is also a Boolean degree 2 function. And you need 4 input coordinates to determine the output. Okay, now maybe you think we need an arbitrary amount of input variables, but that is also not true. For a degree 2 function, we need at most 4 input variables. Here you have a complete list. And of all possible examples for Boolean degree 2 functions. this list was first determined, motivated by cryptography by Claude Calais and others in 1991, not written in this notation. And you can make a similar list for degree 3 functions, where students of Paranikov, first by computer and then by hand, gave a list of all the degree 3 examples. Okay, so what about general degree D? You can say that whenever you limit your Boolean degree D functions on the hypercube to a certain degree, it does not matter how large your hypercube is, it only depends on a constant number of coordinates. And this is known as, or sometimes called, the Nisan-Szegedy Theorem, where they did show in 1991. I think there are 3 mathematicians, Szegedy in Hungary. This is Mario Szegedy, if anyone asks. And here a Boolean degree D function depends on at most d times 2 to the d minus 1 coordinates. You cannot, it's easy to see that you cannot do much better. You need at least 2 to the d because you can have a depth d decision tree. And recently there has been some progress. You can get rid of this d here and replace it by some constant so that the number is 2 to the d. Now, what I like about this topic is that many people worked on the same question without knowing about each other. Like these people do theoretical computer science. Calais and Paranikov do cryptography. And Paranikov actually had the same result in 2001 or 2002 without knowing about this result in 1991. And in this paper, where they got this 2 to the d bound, they also gave a construction of this size, which is exactly the construction Claude Calais and Paranikov already gave in 2002. So for this paper, here Paranikov was 16 years early, and for that he was 10 years late. And only a few years ago, these 2 groups of people realized that they are working on the same topic. So let's say these people are cryptography and these people are complexity theory. Okay. Yeah.
So, so if you restrict the class of the Boolean functions, then can you get a better bound than 2 to d? Are there like research on this?
I don't know what you mean by restricting the class.
Right. I mean, like instead of like considering all possible Boolean functions on the hypercube.
Yes.
Like you try to restrict the Boolean functions which satisfy certain properties, and like then try to improve the upper bound about like.
I'm unaware of anyone who was interested in special examples. One thing that happens is that usually the cryptography people actually care not about, I mean here, everything in my talk is about the real numbers. Cryptography people usually care about F2, the field with 2 elements. It just happens that all the things behave the same way in both settings, and all the proofs you can interchange most of the time for this particular type of problem. But so that is one possible variation I can think of. But for everything I talk about, these things behave the same, and I'm not aware of anything. Anything beyond that. Okay, so now maybe you think being strict with your degree is a little bit too much to ask. You can ask for an approximate result, you can ask for a stability result. And this is sometimes called the Friedgut-Calais-Naor theorem, where you can show that if a function is Boolean and almost affine, so all the other coefficients in your polynomial are very small, then it's actually close to one of these 4 examples. And you have a similar result for general degree D. Okay, now continuing my motivation, why this is an interesting topic and why I like it. Many people investigate things that fall under this framework using a lot of different names. These are not always the same thing, but maybe when you do graph theory, you like equitable partitions or regular sets. If you are into coding theory, you like completely regular codes. So a lot of different words people use, and sometimes they investigate the same problem here. Okay. Now, this is all I want to say about the hypercube. I want to move on to different settings. So in the hypercube, we have a lot of results, and we understand it well. One thing one can investigate is what some people call the slice of the hypercube, or I would say you have the k element subsets of an n-element set. So you take everything of constant weight. And I'm, at least historically speaking, a finite geometer, so I usually care about finite vector spaces a lot. And you can ask the same thing about k-spaces in a finite vector space. You can also ask about the non-uniform setting in finite vector spaces, but I think that is less interesting in this case. Okay, and these are the 2 things I want to talk about. Now, if we restrict ourselves to weight 2 subsets, so here we have our hypercube, we only take weight 2 subsets, then it turns out the first question is, what are our Boolean degree 1 examples? It is not much more interesting. You need to introduce some small condition on n minus k and k, and then you figure out that your list of examples is precisely the same. You just have these 4 types. Everything depends on at most 1 coordinate. And this was rediscovered many times as part of more general results. I mean, this is easy to show. And say, Meyerowitz was probably the first one who wrote it down as part of a more general result. But this is a bit hard to read. You can read a paper by Bill Martin, which I think he actually wrote when he visited South Korea in 2004 for that. And you have one result which only shows that for k divides n, because the authors had a more dogmatic definition of what they wanted to investigate. And yeah, so you can show the same result here. And you have the same examples. Okay, now what other types of results do we have? We have that for the hypercube, if we are Boolean and almost degree 1, then we are almost one of these 4 examples. That is also true for k-sets, except that now it could be a sum of these examples, depending on what the value of k is compared to n. And you have that for the hypercube, if you have a Boolean degree D function, then it depends on a constant number of variables. So the number only depends on D. And when you impose some restrictions on k and n minus k, then you get exactly this bound, gamma of D, it's called here also for your Boolean degree D function for k sets. As soon as your k and n minus k is bounded away from 0, sufficiently large, and you have a stability result of that. There is an unpublished result that only requires n minus k to be large enough, I think it's still unpublished. At least I did not see it anywhere. And then Yuval Filmus, not too long ago, did show that if you do not care about getting the same number as the hypercube, but you just want that there is some function which makes it independent of your n, then you only need that k or n minus k is at least 2 times your degree. Now, here he uses a nice Ramsey argument, which says that some number is finite. So I think the number you get out of his proof is nothing nice explicitly. So like say for d equals 2, here we have 4. While here for d equals 2, I think it's a gigantic number because you rely on this Ramsey argument for which you don't have any reasonable bound. And at least these 2 numbers cannot be the same because I know at least one example. I think by now there are more examples. Some people found other examples. But for n equals 8 and k equals 4, I know for d equals 2, there's an example with 5 relevant variables, not just 4. So there are 2 different problems. You can see when you get the bound from the hypercube, and you can see when do you get some bound. And you always need this at least to n2d condition, otherwise you get some free constructions. Okay, so this is my first very short mentioning of Ramsey results. Now, moving on to vector spaces. What do we have here? Now here you have the subspace lattice of a 4-dimensional vector space over the field with 2 elements. And this is one of the reasons why I like to give this talk again and again, because many years ago I spent a lot of time making this picture. Now I have to use it often enough. And what do we call degree 1 here? So we have a ranked lattice or a poset, and here we have rank 0 elements, rank 1, rank 2, rank 3, rank 4. And what is degree 1? We use our rank 1 as variables, and then we pick some other layer, and we want to write, say, 2 spaces, families of 2 spaces as a function using these 1 spaces. So that is degree 1 here. But now you might know that vector spaces are self-dual. I can flip it around and it will be the same lattice. So instead of using this layer of rank 1, we could also use the layer of rank n minus 1. And we would get the same definition of degree 1. So we can use either the 1 spaces or the hyperplanes. And I'm a projective geometer, so I often see 1-dimensional subspaces as points, just that you're not confused why I call it P. Okay. What are our examples here? We can take all the 2 spaces or all the subspaces incident with a 1-dimensional subspace. And that is that example. And we can, of course, take the complement. Then, I don't know if the switch to the colors of my university was good, because I think it's a bit hard to see sometimes. We can fix 1 hyperplane and take everything incident with it. Another example of degree 1. And then what is the last thing we can do? We can take a 1 space and a hyperplane, which are not incident, and we can take the union of both. And then we have this list of degree 1 examples. 8 in total. So it's a bit more interesting already than the set case. And I mean, the reason why it's more interesting is because in vector spaces, taking complements and taking the dual of something is not the same. For sets, it's the same thing. Okay. And surprisingly, this I think is the oldest problem in my talk, because it was first investigated by Cameron and Liebler in 1982, who were motivated by group theory and who were motivated by this question, which is written down, then there's no question. You look at the action of subgroups of P gamma L for Q on your four-dimensional vector space, then it's easy to see that the number of orbits on two spaces is at least the number of orbits on one spaces. Or projectively, if you look at the three-dimensional projective space and take any subgroup of your projective group, then the number of orbits on lines is at least the number of orbits on points. And if you have equality, then you always get what I just defined as a Boolean degree 1 function. That is the reason why this is investigated for much, much longer than the other problems I have mentioned. And now I'm slightly lying. Cameron and Liebler made a conjecture. I think they made this particular conjecture only for n equals 4, but they made a second conjecture which is for general n, so I think they also thought about general n here, and two spaces. They made the conjecture that these are actually all examples. We don't have any others. We just have these easy constructions. And that would be nice. And it's a good conjecture to make because it's true for sets, and it's true for the field with two elements, which is also not too hard to see. But sadly, there is a counterexample already for the field with three elements. And nowadays, we know many, many counterexamples. So people spend a lot of time on the setting where we have n equals 4 and k equals 2. And here another slide to trying to convince people that it's an interesting topic by mentioning many people who have worked on that topic. People spent a lot of time finding more counterexamples to that conjecture, and there are still some open cases like I think we don't know any infinite family for fields of that size, an even power of 2. But in general, by now, it seems that there are just many such examples. All for n equals 4 and k equals 2. Now, moving on, there are restrictions on the possible sizes for such examples, and there are also several results in a more general setting, where you go to general n or general n and k. But you can see that people are stuck in the four-dimensional case a lot. Okay, so what do we know about general n? Now I'm wondering about my pacing. Maybe I'm too fast. You can interrupt me if you have questions, please. Now, if we have a Boolean degree 1 functions on k spaces for n larger than 4 and k equals 2, then we have solved up all the cases up to q equals 5. How did all these proofs go? The proofs go in the way that you have, you always have the setting that for n equals 4, you always get funny examples. And then you want to show that for n equals 5, you no longer have funny examples. So what do? You classify by computer all your funny examples for n equals 4. And then you show that you cannot use any of your funny examples in larger dimension. Because whenever you restrict to dimension 4, you know it is in your finite list of examples. and then you try to put them together like a Sudoku puzzle, and you can show unless you have one of these examples, it does not work. Naturally, the problem is that it's an infinite number of finite fields. So maybe you have to classify all of these things, and q equals 2 and 3 are easy. 4 and 5 definitely needs a computer and some tricks how to do it efficiently. Probably you can do q equals 7 and maybe 8, but it will not solve the problem, sadly. And then you rely on a computer classification to get your induction started. So you do induction, but your first step is a terrible computer classification. Okay. Now, these people did not care about general K, but when I visited Yuval Filmus many years ago, in a surprisingly short but productive visit, I figured out that he cares about that problem, but he did not know about all these previous results. He knew this result for q equals 2, but general K. And then we figured out we can also do induction on K to do it for the same small values of Q. So even degree 1 there is complicated. Okay. And then I thought about this for many years, and I did not make any progress. But in 2023, I learned about vector space Ramsey numbers. Maybe I knew about vector space Ramsey numbers before, but I did not care about them. But at least in 2023, I learned about vector space Ramsey numbers. And my paper is very short, so it does not reflect how much I thought about this. I thought about it for many months. And then I figured out how you can use vector space Ramsey numbers to at least get an asymptotic result, where when n is at least 2k plus some constant which depends on q, then you only have these 8 examples. Now, you are the first audience who sees the statement written in this form. As you can see in this footnote, I have rewritten it many, many times because people complained, I complained, or people misunderstood my earlier statements. Okay, so what I want to talk about for the rest of the talk is what is the idea of this argument. And I still seem to be quite fast, so I apologize. The proof relies on 3 things. First of all, you have old structural results found by people in finite geometry who care about these problems, which is, you can look at some subspace of your vector space, and if your function locally looks like that example which only depends on one space, then you can show that your function must be globally like that. Similarly, if your function locally looks like it depends on only one space and one hyperplane, then your function will look globally like that. Now you feel like it's missing that if your function locally looks like depending on only a hyperplane, then it must look globally like that. But of course something like this cannot be true, because at least you could have this example globally where it also depends on one space, which is just not locally covered. You could also look at dual statements, then you could flip P and H here, but it's hard to combine. So, and I don't think you can combine this statement with its dual statement to get anything useful. Okay. And then it's also helpful to know that if you're not one of these examples, that in some sense you are far away from these examples. These examples are all very small, and all these counter examples which exist for n equals 4 they are actually quite large. They are usually 1/3 of all vertices, if you think of it as a graph, or 1/2. Okay, so the second part is that you use that Ramsey numbers for vector spaces exist. I will define them more on the next 2 slides. And the last point, maybe it's not necessary, it's just convenient. You can restrict all your investigation to k equals 2. And yeah, I find it always a bit strange that the thing I did not know about is the oldest thing in this list. And which helps. Okay. And maybe I should say one more thing about this result here. I'm not too happy that you have a dependency on Q, but at least when I talk to Yuval Filmus, he is very happy about that because he does not care about non-asymptotic behavior. So he is happy as long as you fix Q and your n is large, then at least him and his friends are happy. Okay. Now, here you have the best projective plane, the Fano plane. And can you color the points of a Fano plane? So a Fano plane is, of course, you have a 3-dimensional vector space, you have a field with 2 elements, lines are the 2 spaces, points are the 1 spaces. Can you color it with 2 colors without getting a monochromatic line? Does anyone want to make a guess?
The fact that you're asking the question strongly pushes in one direction.
Yeah, probably. I mean, when you color this one, and this one, when these are just 3 points in general position, then you still have this line uncovered. But you cannot add this point, because then this will be 1 color. You cannot add this point, because this won't be 1 color. You cannot add this point, because then this would be 1 color. So it does not work. You cannot do that. And so what we can see is that the Ramsey number are 2, 2, 2 equals 3. I did not tell you what that notation means. I'm sorry. This means we have a field with 2 elements. This means we care about 2-dimensional subspaces. This means we have 2 colors. And as soon as we have dimension at least 3, we will always get a monochromatic 2 space. And here you have a more formal definition of the vector space Ramsey number RQSM. So whenever you color one space of an n-dimensional vector space, or if you prefer points of a projective space, and you make your dimension large enough, then you will find a monochromatic subspace. And this you can prove using the Hale-Stewart theorem. There are several proofs of that result, all use Hale-Stewart. And the oldest one is from 1972. And it also works for similar structures, like you, instead of projective spaces, you could say affine spaces is also fine. So you just remove from hyperplane. Good. So how does this help? Here an example for Q equals 2. So when you look at this list of examples, say if you only look at the first half, then if you write it as a polynomial in x degree 1 affine function in xp, then I forgot one entry here. Then you can only get 4 possible entries. So these examples only give you a very restricted choice of coefficients for your polynomial. And now what you want to do is, if you have only the coefficients occurring in these polynomials, then you can show that you are one of these among one of these examples. So what you want to do is you want to take one of your one spaces, which here is a point because I'm thinking projectively, and you want to figure out what is the coefficient of my point here. And we want to show that it's one of these normal coefficients, not some other coefficient. And one can do a stupid argument for q equals 2 that we can have at most 896 different coefficients occurring in our polynomial, but this is not a practical number because we don't want to see in what ways we can use 896 different coefficients to solve anything. And for a larger q, this will get much larger. So what do we do? We use the Ramsey result that when our dimension of our vector space is large enough, then we will get some monochromatic subspace of any dimension we wish for. So this number is probably already very large, and we find this monochromatic subspace. Then we want to slowly go to smaller and smaller subspaces, but we control the coefficients or the colors in all our subspaces. So we look at another subspace here called H2. And if we make H2 large enough, then the intersection of H2 with a span of S1 and P will again be monochromatic. So we just need that S1 is larger than this Ramsey number. You can already see how this is a terrible bound on n because we have a tower of Ramsey numbers, where each Ramsey number, the best bound in general known, is based on the Hale-Stewart theorem. And then we repeat that process. So here we have our monochromatic S2, and then we look for one more monochromatic 2 space in there. And what is the picture that we get here? This is slightly a lie, but you can think of this as a Fano plane. How do I want to draw it? I have to fit the orientation of my slide. My slide looks like that. Here we have our point P. And we have a Fano plane. And say here is what is left of S1. Without loss of generality, we can assume that all the coefficients which happen here are 0. Then we have S2, and everything here will be 0 or 1 over q. Same here. And now we already know 5 of our 7 points of the Fano plane. And then we can also figure out for this point, it must be 0 or 1 over q. And after doing this recursion, we can calculate what P has to be, and we are done. And then we can see that in total we have only 8 possible coefficients, and then we only need the result that if we are among these 8 coefficients, then we are one of our examples here. Okay, now this is nice because we know that for n large enough we cannot find more examples, so at least a lot of work by other people became useless, which made me happy. But you might not be happy about the bound. Say, for q equals 2, we know that it must be 0. Now, in general, there are no good bounds on these vector space Ramsey numbers, I think. The general thing is just that you have this Hales-Jewett type argument, which is terrible. For this particular case, I hope I'm representing that bound correctly, because I did not want to write down the precise bound. Here you have new up arrow notation, so one more than taking exponents. That is the bound you have there, and now we can compare. What we get roughly with that bound is we know it should be 0, while the number the proof gives is written here. It's a very large number. It's probably far away from the here it's far away from the truth, but in general this bound is very bad. And the question I have here is simply, is our, for q equals 3, 4, and 5, it has to be 1. My question is, does it ever get larger than 1? Would be a first question I have here. Okay, so let me give some more motivation at the end of the talk. I'm done with the argument how you show this. The first one motivation is for the proof of the 2-2-2 games conjecture. So the unit games conjecture is about, is it you want to approximate an NP hard problem? Is it hard or not? Or can you approximate it well in polynomial time even if NP is not equal P? And there has been a breakthrough result on that some time ago. And actually what they did do is they investigated functions on the Grassmann graph over the field with 2 elements, where you are not degree 1, you're also not close to degree D, but where you have a significant mass on low degree. So your low degree coefficients are somehow large. And then you can show that such a function is not equally distributed in your vector space, but it has to be concentrated, it has to be sandwiched between, it has to be subspaces A and B, where you have more than expected elements of your function or much less than expected values. And this was what you had to show the proof of the 2-2-2 games conjecture. Just to illustrate why some complexity theory people care about these questions. And then I do not think that people care much about that here, I don't know. Another corollary of that is that you can look at 2 intersecting sets in vector spaces, which means you have a subset of points such that any K space either contains A such points or precisely B such points. And maybe you have heard of hyperovals, I don't know. And it is a very long open problem. You know for a very long time that many of these sets exist for n equals 3 and k equals 2, or for n k equals 2. And you know for n equals 4 and k equals 2, or any larger n and k equals 2, this can only exist if q is an odd square. So the smallest case is q equals 9. and this is a problem open for over 50 years, I guess, given that it's we have now 26. And at least you can show that for large enough n, these do not exist. Okay, so let me conclude with a few questions. The one question you already know. What is the behavior of this function such that all examples become trivial? When does it start? And for that, already getting some decent bounds on vector space Ramsey numbers, I think, would be interesting. I don't know if these problems are actually related or if it just feels like that. Looking at my proof, I feel like it should grow in Q because my proof requires that, but then I don't know. Now, for sets and hypercube, I talked about general degree a lot. Even getting some result for degree 2 seems to be hard here because, again, there will be funny examples in small dimension. So, and now things are so large that even for Q fields of size 2, you cannot have any hope of using a computer in a reasonable way. So you would need to, and you cannot transfer the techniques because they rely on knowing all examples, and you, in general, you do not want to list all possible examples. So getting a Nisan-Szegedy type theorem, let's say even for degree 2, would be an interesting question here. Okay, and I recently wrote a survey article on this set of problems, if you want to have a written summary. And that is all I wanted to say. Thank you for your attention.
Any question?
So in here you consider the finite field, then can you replace the finite field to some link field?
Replace it by which kind of field?
I don't know, but some kind of links, because I don't know where the properties of the field was used in your proof.
In my proof here, that's a good question to ask when you can replace a finite field by something else. I mean, I use that you have this Ramsey result.
Yeah, but the Hare-Street theorem does not require the finite field.
I'm sorry?
The Hare-Street theorem does not require the finite field, that kind of things, isn't it? Maybe I'm wrong.
I mean, in this, I mean, Hale-Stewart does not require a finite field, but in this, in this application, I mean, we use that there is a Ramsey theorem for finite fields. I don't know how that would, I would not know what happened. And also, at least for the degree 1 case, I could just write down all coefficients which occur, which does not depend on, which does depend on the size of the field. I'm just not sure what will happen there if you replace it by something else. Even how to define it properly is not completely clear to me without thinking a bit.
Thanks.
I was just curious, why the name M. Junta?
Why N. Junta? Because, okay, I mean, these are the Israeli names. And I think originally when it just depends on one, you call it a dictator because only one person decides, only here coordinate 1. And then when you replace a dictator by, say, a military junta, then you have a group of people who decides. So say for a degree 2 function, you have 4 people deciding at most. And that is a generalization of a dictator. That is why they call it that way. That's easy to answer.
So for Grassmann graph setting, can we prove some theorem like a free-dot hunter theorem? How to define the sensitivity or influence of this setting?
Yeah, that is a harder question to ask because of I don't know how to define that in a good way. That is why I restrict myself to, I mean, what makes sense is an FKN theorem because there is no question about how to define it, and Nisan-Szegedy also makes sense because then we don't have to think about the definition. For all the other things, for most of the other classical questions, I'm not sure what is the best definition. That's my generic answer.
So can we define some a derivative of the Grassmann graph? Because the sensitivity is the average of sum of derivatives.
Yeah, but then in vector spaces, what do you mean? Do you want to take quotient spaces? Do you want to just remove some part of your vector space without paying attention to the geometry or the algebraic structure of it? Do you want to do the dual thing of in taking hyperplane sections, which then again is something else than taking quotients for sets or hypercubes? That's the same thing. Like there are so many things which are the same for sets where you then have to decide, are they still the same in vector spaces, or what do you mean? That in general, I mean, if for any such notion you can find a proof which works well and shows something interesting, then I'm happy about that idea. But I do not have such a thing, so I don't know which definition I think is a good one, if that makes sense.
Any other question? Okay, if not, just thank you.
So, who's going for dinner? Raise your hand.